The expert talk for the next session is by Shri Pradeep Nair. Shri Pradeep Nair is Vice President, Hardware Sales at Intech Additive Solutions, Bangalore. Shri Nair is credited with bringing in additive manufacturing to India and Southeast Asia way back in 1996, when this technology was in its infancy. I invite Shri Nair to share his expert talk.
Thank you. End the presentation. Good afternoon, and welcome to the post-lunch session. Normally this session is what we call as the graveyard shift for speakers. You know, after a good lunch, all these look like comfortable beds. So, you know, it's my job to try and keep you engaged, and I hope you find this talk interesting. My name is Pradeep Nair, and thanks for the introduction. Yes, I've been with additive manufacturing for a long time. Initial days, it did start as a technology that managed thermoplastic materials. And progressively, it moved to metals. And so I spent most part of my additive life working for an American company like Stratasys, and then moved to a German company called SLM. And more recently, for the last 18 months, excited with an Indian technology, an Indian company producing, not just producing, designed, developed, and manufacturing India-made metal 3D printer has been a revelation for me. Actually, I was listening to Dr. Satish Reddy, who was pushing the industry, Indian industries, to make powders and the printers themselves out of India. I wish he was here, because I would have told him it's already happening. So it's not in the future, it's right here. So what my interest today is, I don't want to spend too much time. By the way, I wasn't given too much time by Dr. Sarkar. I think because Navratri is around the corner, he gave me a 50% discount, asked me to reduce my speech by 50%. So off went a lot of slides. So I'm going to skip parts of my presentation, which I'm sure many of you are already aware or can easily find in the net. So one of them, for example, why do you need metal AM? I think speaker after speaker in the morning told you the importance of metal additive manufacturing. But in a nutshell, it offers unparalleled design freedom compared to your machining, which we call as subtractive manufacturing. So you look at subtractive and additive. Additive gives you a lot of design freedom. If you can design it, you can print it, right? Dr. Jha said that, the very same words. So whatever you can design, the machine can print. In other words, you design for, not for manufacturability, but you manufacture for design. So that is a key issue with additive. And also, now the range of materials are increasing. Way back in 2000, when the first machine showed up, you had only almost a primitive, steel material. But from then, we've progressed a lot, and we'll talk about that. And because of the design freedom, the components that you could not make some time back is now manufacturable, and which means a new subject, relatively new subject for DFAM. So you all used to design for manufacturing. Now it's designed for additive manufacturing, which means right at the concept level, when you design a component, you're designing without the constraints of machining. So you're thinking differently. You need to think differently when you make additives. So going back to point number 2, components not possible. We have a problem again. Yeah. Now this, it's the laser pointer's turn not to work. All right. Okay. So since components that are not possible some time back is possible now, so you can think differently. That's what DFM allows you to. And which means now, because additive addresses low volume production, it's not really a technology for millions of components, but when you have low volume, high complexity, additive is fantastic. So which means that you can keep digital libraries now instead of keeping thousands and thousands of parts. I was talking to HAL. One division of HAL has 90,000 parts in spare. And they keep this for decades. So they have this whole buildings full of spares, which may not be used for 20 years. But the 21st year that spare is required, they have to pull it out. So that's a lot of space, time, and money. Now the idea is veering towards, why keep all that? Let's just digitize it and print as and when required. So that's spares production on demand. And of course, when you look at small volume, the cost and time advantages of what additive can bring in is huge. So I won't go too much into that, or the application side. I'm sure you can Google up a lot of that, because I really want to talk about a subject that was, pervading from the morning, Atmanirbhar Bharat in additive, and I want to talk about that in additive. So, but just a rough few examples. For example, this component, this, as you can see this is virtually unmachinable. No way you can produce that with conventional manufacturing techniques. But since the part was so huge, we couldn't build it in a single print. So we did it in segments. We printed 8 pieces and then fastened them together. Now, the benefit of that is that this part is not possible to be machined. And then the requirements, your early stage of design, you want to test these parts, and you need just a few. So how are you going to kind of tool up or machine just for 3 or 4 of these? So metal additive is a perfect solution for that. And any design changes, if you're tooled up, any design changes, your tool is gone. That's probably a few lakhs, thousand, probably if not more, worth of tool just thrown away. Compressor turbines. Just have a look at the geometry. Imagine machining this. Some of you mechanical students out here, just think of how you're going to machine this. Extremely complex component. However, for us, it's a 124-hour job. Now, what you want to think about when you see this part, it is all done in a single machine. If you were to subtractively or machine this component, how many machines would you need? A whole array of machines, a whole array of processes, a whole array of different skills required to manufacture this component. And that's going to take you weeks and weeks of manufacturing, whereas we just print this out in 125 hours, glass bead it, and you almost get this kind of, this is the finish that you get, not right out of the machine, but after post-processing, you get this kind of machine, right? And this component, we ran at 12,000 RPM, so which means that it could go to the final component, into the final assembly, and actually function. A good example of flame tube, the material is in kernel 625, and 465 diameter. It's a complex component, very expensive, and it's an aerospace component. So what we did is we printed in 5 pieces and welded together. So again, the important thing is, remember this is early stage of design. So the designers want to test different kinds of design. Trying to machine this is not a good solution. Additively made, as you can see, it's just 250 hours. And we could print different kinds of iterations, different kinds of designs, test it out, choose the best design, and then go in for production. So this is a critical enabler for not just that speed or the cost, but also ability to work with multiple designs, which means you choose the best design in the shortest possible time. No talk on additive is complete without talking about the benefits of conformal cooling. If you Google up, you'll see a lot of examples of how additive is changing tooling applications by this thing called conformal cooling, where normally what you do is you have a tool and then you have cooling lines running across in straight lines. So they're good, they do the job, but not very effectively, because you want cooling to happen right at the surface where the, let's say, the plastic or metal meets the mold, so the cooling is right at the face, which means you can have a higher ejection rate of parts. So additives, since we are adding material, not subtracting material, allows you to put the cooling vents right at the face. So you look at the cooling channels here. This is the existing design. See the new design where the cooling channels are right up to the face. There's the skin of the metal, which means cycle time dropped almost 40%. In other words, just by doing this, production increased by 40%. That's a big benefit. And no example is complete without a human element, right? A human interest story. So you're probably already reading, of course, for queasy people, this is a little tough to see. But you probably are reading a lot about how metal additive is changing the life of a lot of patients by allowing implants, customer-specific or patient-specific implants like this. Titanium implant on the skull of a patient, or there's a hip implant. So the difference is that previously you would get 4 or 5 sizes made by Zimmer or Stryker Medical. If you wanted a knee surgery, a kneecap would be bought from them. You had 5 standard sizes, and you prayed to God and implanted one and hope it is your size. If it doesn't, then over a period of time, you'll develop some aches, and then you probably go for the next size. It's a process. Whereas additively done, we're scanning your original bone or cap and printing one exactly in titanium, so that once implanted, it's good. It's good for life. So this is really changing the way the implants are being done. And I'm glad to say that we have very many examples of this happening within India, including implanting of a vertebral bone. And a 34-year-old woman who was facing life to be led as a vegetable, and we 3D printed a bone for a vertebral disc, actually, and she's back to normalcy. That was something very heartwarming, I must say. So that was some basic examples, but I'm coming back to my topic on Atmanirbhar. So this is a global growth of metal additive manufacturing. Now you can see the initial years. Somewhere around 2000 onwards, this growth was really slow. Not surprising, because the early days, and frankly speaking, when I joined additive in 1996, and around 2000, somebody had asked me, do you think you'll be able to print metals? For me, it was alchemy, honestly speaking. I would say, no, I don't see metals happening. I think this is one thing I'm very happy to eat my words. Metals are happening right now. So as you watch the growth, you start seeing a sudden spurt, especially over the last 4 to 5 years. That's because more powerful lasers are coming. Those days we used to work with 100-watt lasers. In fact, before that it was a 20-watt CO2 laser, hybrid lasers. So we moved to solid-state lasers. Now it's ytterbium fiber lasers that work at 400 watts. In fact, the iFUSION SF1 downstairs is a 500-watt laser. So that means the laser is powerful. It allows you to melt increased number of materials, which means new applications are emerging. And thanks to multi-laser, material costs coming down, and I think, again, going back to Dr. Satish Reddy's question, powders being made in India, it's already happening. A Bangalore-based company called Indomem is already manufacturing powders. They have gone up to 3 powders and will add more. But the story doesn't end there. Intech alone is looking at, in the next 18 months, making 50 powders available on this machine. 50. Our list is actually 100 plus. So that means there's a wide range of materials that need to be made, but made is the end product. There is a whole research that has to happen before that. Before that powder can be really made for additive. So more applications are coming. Yes, this is global scenario. Coming up. So, there you go, sir. So, MAM stands for Metal Additive Manufacturing in this case. So, looking at India's situation, the first machine was installed in India in the year 2000. at CMTI Bangalore. And since then, in 21 years or so, we have just got 130 machines installed, right? So, not a great number. That's, if you look at it, it's roughly about 6 machines a year. So, how do we do in comparison? China probably installs something, we are 6 a year, China probably installs about 20 a month. So, I think we shouldn't compare at all. So, we are really behind. But the good part is that approximately 70% of them were sold in the last 5 years, which means the importance of metal additive manufacturing is now being felt. And it's only going to go up because of a few factors. Okay, these are statistics. So when you look at it, medical tooling, so now medical is a loosely held term here because this is mostly dental implants, crowns, caps. Trust me, in about 24 months down the line, all your crowns and caps will never be casted, or traditional approach will not be there. They'll all be 3D printed. So you got more and more labs investing in it. Dent Lab in Cochin in Kerala is the largest dental lab in the world. They have a huge amount of machines. There are 30,000 employees churning out dental parts. That's all they do. And so that's a huge emerging application. But this is a key. As you all know, probably the Prime Minister has moved 110 items away from import list and now has to be manufactured within India. That I believe, will spur additive manufacturing in a big way. Okay, again. Okay. It's a little slow to respond. So when you go back in this issue, we see that very little machines installed. So what's happening to us? Excuse me. Next slide, please. Yep. So a few points to ponder between us. We missed out on the third industrial revolution. We're talking, in fact, Dr. Manohar mentioned that the university is built around 4.0, Industry 4.0. And this is a critical area that we want to get into, and I believe, strongly believe, additive, and especially metal additive, is a key component of Industry 4.0. Some of the things InTech is developing is very much aimed at this particular manufacturing philosophy which lights out. So COVID taught us that a pandemic shuts down everything. Industries, gone. So how do we start manufacturing despite COVID? So we're looking at technologies that will enable that, where you have automatic pre-processing, manufacturing, automatic post-processing, and parts come out, and you could control this whole system using your iPhone or Android for that matter. So that's Industry 4.0 enabling that. But you look at this, we missed the third industrial revolution. So even though we are the world's number 2 in cell phone manufacturing, how much of it is our own? We're just assembling, right? How much are we designing and manufacturing? Very little. Then what we did was, government said, okay, liberalization, we want technology to come in. So we started signing up. Many foreign companies started coming into India. And, but look at how much we invested in research and development. Our own industries, in terms of public sector or private, how much did we invest in this critical area? Not much, really. So we went from farming economy, we missed out industrial economy, and we missed the manufacturing, and that's really, hurting us in big way. And it's kind of, you feel, next slide, please. You feel it's, it's almost frustrating. We can't really catch up with these, with the foreigners. So we started bringing in these foreign companies, and a lot of FDIs came in. It does help somewhat, but how many foreign companies give you their key technologies? They don't. They keep them offshore. And I know HAL does a lot of work for Airbus, but if you look at the components they manufacture, they're the doors for a A320, where they just, designs come in and they just machine them. That's it. So there is no design element that is happening within them. the funny part is there are companies like down my road where I live, you have Safran, your Honeywell, all of them in a row designing aerospace components, Daimler Chrysler, all of them making, Daimler rather, making highly advanced designs by Indian engineers and going elsewhere. There's offshoring here. We do not know what the technology behind is. Each one is in a silo doing one piece of the technology and he doesn't understand what's happening in the next door. So we're going to get foreign investments, but we're not going to get designs. So obviously the key is not foreign investments. It is not foreign technology. It definitely is. It's an indigenous effort, including investments in local R&D and manufacturing. We really need this if we truly want to be Atmanirbhar. This is a good study I read a while back by Raghunandan. This came in Hindu newspaper. It's fantastic. It was an excellent article. So, in other words, we missed the manufacturing bus. There are countries that are far ahead of us. So how do we now step over that and go to the next stage of Industry 4.0? We need to invest and grow a method that will usher us in the next manufacturing era. And what is going to be in the next 5 to 10 years focus of India? Definitely a lot of defense and aerospace applications are going to come to the forefront. And if you look at one technology that meets this, is definitely additive. So is additive going to be the next revolution? That is the question. So I don't want to again spend too much time. I believe I got 20 minutes. So additive meets this requirement very well. I've talked about this low volume production, lightweighting, etc., etc. So these are key to the next generation of manufacturing. But look at what we're doing. You look at how much we're investing in this. As Asia, if you look at Asia alone and look at the additive market size, we invest only about 3 to 5% of all machines installed in Asia is in India. Now that compares, when you look at manufacturing as a percent of GDP, Australia probably has, for every one industry or organization in Australia, manufacturing organization, we have 100 in India. That's the kind of ratio. But you look at the number of machines they have bought and we have bought, and look at the GDPs, manufacturing as a percentage of GDP. While we are ahead of Australia, look how little we are investing. So why are we doing this is a good question. So what is inhibiting our investments? Let's face it, we are traditionally a conservative country, right? We don't rush to invest in new technology. We wait, we watch, and we generally come in much later. The world has invested and gone ahead, and then we slowly start going towards that direction. So, but then I'm not convinced that's the only reason. And I strongly believe again that there's a lot of interest in metal 3D printers. But here's the problem. I think this was mentioned in the morning session. All metal 3D printers were imported so far. So a small machine was minimum, the cheapest machine with hardly any good specifications was 2 crores. Mid-range was 6 to 7 crores, and bigger machines from 9 to 15 crores. Really, how many companies can afford that in India? Really. And story doesn't end there. It's subject to duties, transportation insurance, put another 25%, add more for site preparation. So it's a pretty expensive proposition. And when you looked at the break-even or return over investment, it was very, very challenging. Our defense has the money to invest in 3D printers. But here's the challenge. If you were to import a machine from Germany or let's say USA, you had to sign an end-use agreement, which restricted you from, if it's US, it's you have the ITAR, or if it's Germany, you have the BAFA, which restricts you what you can use it for. For example, Professor Ganguly wants to use it for nuclear fuel applications. It's a no-no. You cannot use it. If you buy the machine, you spend 12 crores, bought a machine, and tomorrow somebody said, hey, that machine is getting used for nuclear applications. That's it. Service is gone. Support is gone. No powders, nothing. Your 12 crores down the drain. So, and not just nuclear, military too. If you use it for missiles, tanks, guns, or any kind of these applications, they prevented you. So they sold you a piece of 12 crores or 2 crores or 5 crores, and then they told you how you can use it, probably, to make prototypes, which is not really what you want, right? So that inhibited us from investing a lot more. And another big problem was that you bought the machine, and when it broke down, you need components to come from US or Europe, and your machine could be down as long as 2 to 3 months. So this really did not excite the Indian user that much. So it kind of feels like the end of the road, right? Of course, you did see Chinese machines. They're cheaper, but they use Chinese lasers, Chinese optics, and automation. And, by the time we deliver it to you, if it's working, good luck. So that's typically what Chinese machines. And besides the fact that they have broken all the IPs and patents, and they really can't go out of China barring 1 or 2 manufacturers. So it kind of sounds that, are we going to see hundreds and hundreds of metal 3D printers in India? Doesn't look like it. So next slide, please. Okay. All right. So I saw this quote by Alan Kay. I don't know how many of you know Alan Kay. He is the person who invented OOPS language, and also the graphic user interface, as you know today, has been, the first GUI was designed by him. So Alan Kay says that people who are serious about their software should build their own hardware. So where's the software element in this? Intech actually started our journey as a 3D printing services company. We printed parts for other organizations like HAL. So somewhere in 2017, we were struggling to make, it's not simple like you can make a metal powder and make it run on a hardware. There are 248 parameters in a machine, and you have to program all 248 parameters to successfully run the powder. That's a challenge. So every time we wanted a new powder, we had to go back to EOS or SLM of Germany, pay them 30,000, 50,000 euros, wait for 6 months, 8 months before you could get a parameter. So we decided to automate that. We started writing our own software called Optomat. So we started writing, then we decided to make our own print control software. So while we were doing that, AM Optomat and AM Builder, we decided, why not get into designing? When I say we, Sridhar Balram, my CEO, he decided to invest in developing an Indian printer. Now, I would say that was quite gutsy, because at that time, back in 2017, nobody would imagine an Indian company is going to come up with that. The technology itself is actually quite complex, to tell you the truth. So we didn't think he'll invest in that, but he did. So when we decided to build the machine, one thing we decided we will not compromise. We took the best of the lasers, best of the scanners and automation. That's still German, but the balance of the machine, about 72% or 2,300 components in that machine downstairs, the SF1, whenever you get to visit it, there's 2,300 components inside, and all of them machined with high precision in our facility in Bangalore. While we were designing, we filed our own IPs, patents. So we created the machine is 100% indigenously developed with no patent violation. So that's something exciting. And the good part is, around this time, I think most of you probably know DMG Mori, global giant in manufacturing. DMG Mori saw Intech and actually invested in Intech. So they hold 30% of Intech. But strictly hands-off, we design, we manufacture, and they don't interfere. But it's good to know that a German giant thinks an Indian company, technology company, is well worth investing into. And the result is that we made India's first metal 3D printers, the iFUSION SF1, and which we announced last year. And towards February this year, February 17th, in fact, to be precise, we introduced the LF series. The LF series is a large format machine, which is 450 millimeters. It's a giant part, actually. So we introduced these two machines. We are well on a machine to make, not many ladies here, but exciting news. You can actually walk into a showroom and print your own jewelry. So we should be launching a machine in January that prints actually in gold. Right? That's pretty exciting. So gold, platinum, and probably brass. So we have a machine coming up called Precious that will do this. So we also have a mid-format machine coming up. We also have software solutions like AM Builder and AM Optomed. This is unique, so only one of its kind in the world. So something we are very proud of. So we truly have a homegrown solution in metals. But I'm going to skip this. If you want to see the machine, please, I think you'll have an opportunity to see it downstairs. Now, this is something I want to quickly talk about. In a couple of slides, I'll be out. So we are focused on, really, our core area is to continue designing machines and continue writing the core software to enable our users to exploit the hardware in its best possible form, right? But then there's a lot more to this. There's a lot of things, that technology that goes into the pre-processing and post-processing and even during build that we need that would give us a more complete ecosystem of metal additive manufacturing. And truly, I at heart believe that, in fact, Intech will be a MNC in 6 months. We'll open our offices in Europe, in Germany, and in Singapore or Korea next year, and most probably towards the end of next year, we'll have our first US office. So again, I wish Dr. Satish Reddy was here. He would be excited to hear that actually we got our first international order already. So we are truly getting to be an MNC. So, but then we do have a big challenge. We have additive giants who have been in this field for a long period. And we as a young Indian startup are going to clash with the titans. So where we are focusing on is, we realize one thing: they're all focused narrowly on their hardware and software. And all the subsystems are all third party. So we decided that's going to be our strength. Of course, we also are focusing on consultancy and DFAM services, which we believe will bring a key element in taking a customer from subtractive to additive. But beyond that, we are now focusing on providing our customers a truly complete ecosystem. So an example, the component you see here, unfortunately I couldn't get it here today because of copyright issues. This is a nozzle guide vane. The material is CM247. It's an alloy. And this alloy is very challenging. Currently, the only way you can make parts out of that is investment casting. Now, investment casting, as many of you know, has its limitations. You typically try and do a near net shape. I think nuclear fuel complex, Dr. Srivastava was talking about that. You do near net shapes, and then you have to go through a lot of extensive machining process. But CM247 is not ideal for machining. So we made the powder to run on these machines, which first time globally. There is nobody else in the world who has succeeded in making this component, and it is a collaboration between HL and us. So similarly, we are working with quite a few, IIT, Jammu, PDU, CMET, IIC, in different spheres. We now opened out discussions to work with the industry. But there's a lot more that we want to develop. For example, we still import lasers. Is there anybody out here who probably would want to design lasers? We are very interested. We want to support that effort and work with them in developing our own laser scan systems. We want to develop melt-pool quality monitoring tools, powder management systems, sieving system, filtering systems. There's like a whole host of things. Support, surface finishing techniques, support removal, part qualification. For putting a part in an aircraft, you need a FAA approval, or a SEMILAC approval. That's a whole subject which we can work with universities to enable that. There's material powder, qualification, powder development, application development, a whole gamut of things. There's a lot of work. There's so much work for several universities to come together and work with Intech in developing a very, very aggressive and functional ecosystem that we as a country can take forward and compete in global space. So if this sparked any interest in any of you, excuse me, So I'd really like to invite you all to join our journey in creating this ecosystem. If you have any ideas for projects that you want to work with us, please contact us. Do send us a mail. We want to talk to you. We evaluate your project, We want to talk to you and see if we can have a relationship that is mutually beneficial. And so thank you very much. Thank you for this opportunity to be here and address you all. Thank you.
Thank you, sir. The next speaker for today is Dr. Virendra Kumar Gupta. Dr. Virendra Kumar Gupta, R&D Head Polymer and Senior Vice President, Reliance Industries Limited, is an accomplished scientist and technologist who has successfully translated his fundamental work in material science into technology implemented for commercial grade production for growth sectors such as agriculture, health, transportation, etc. Dr. Gupta is an co-inventor of 200 patents and has commercialized 30 technologies in petrochemicals and polymer sectors. We invite Dr. Gupta to share his expert talk with this gathering today.
Is it my presentation? Okay. Good afternoon to all. My compliments to organizing committee for organizing first international conference on additive manufacturing and advanced material. In the morning presentations, we have listened more about the metal as a choice for 3D printing technology. Today, I thought I should cover the thermoplastic materials, which is also getting a lot of importance in additive manufacturing. Let me first start with a disclaimer that the views expressed in this presentation is my own and bring my own perspective on the trends and developments in thermoplastic materials for additive manufacturing. Reliance outlook for every business is quite exciting. And if you look at oil to chemical, business has positioned for high growth thermoplastic elastomers as well as other materials for different growth sector ranging from retail, health, automobile, defense, agriculture, and others. And this is evidenced from the manufacturing and technology capabilities of Reliance in the area of thermoplastic elastomers, covering polyolefin materials, elastomers, polyesters. And recently, we have also moved into the area of composites and advanced engineering thermoplastic materials development. And these materials are also very important for additive manufacturing in addition to the metals and others for indigenous technology development. Reliance Research and Technology development is mainly carried out at our R&D facilities, which is located in Navi Bombay, with advanced synthetic product application, as well as analytical capabilities. In addition to that, we have also the R&D center at different locations, which also provide us the support for scaling up the technology, process, and product at different locations. Now let me come back to what I want to emphasize in next 15 minutes. The fourth industrial revolution, which is currently happening, it is a convergence of physical, digital, and the biological world. And this is the right time for India to focus in these technology areas which will take India to the next level of technology leadership. Now, if we look the physical part of the fourth industrial revolution, the 3D printing technology in one of the most critical technology, which is a part to bring new innovations or new growth in the sectors relevant to the society. Now, in the 3D printing, it is really, as you heard in the morning, is going to be a next industrial revolutions. And what it does, that what are the informations which are captured digitally through the material choice get converted into the product. And therefore, the additive manufacturing is going to be a critical for niche applications, not on high volume applications, but low volume, but at the same time, very critical. And this is the best example of digital information converting into a products through material choice. And our interest is more in the materials, which is a part of my today discussions, that how Reliance is pursuing the efforts of developing the materials, and particularly the thermoplastic materials and elastomers, which are critical for 3D printing. And as I had heard that in India, in Atmanirbhar Bharat, we should also have a technologies for most of the material to bring down the cost and also not becoming dependence on others. 3D printing applications in a COVID time, I think worldwide is a well demonstrated. Reliance also work on some of the medical devices based on 3D printed wall, and we have successfully developed that. And this COVID time has really demonstrated that how in a short period of time, the technology such as 3D printing application, 3D printing can be useful and make a difference for the societal needs. In addition to that, there are many areas where the 3D printing have unique applications, ranging from your medical sector, the buildings. Today, the 3D printing is also getting a lot of attention technologies for creating sustainable buildings in a much quicker time, in addition to the medical sectors and others. If you look at the market growth, which is going to come, and if you look at the low to high of the 3D printer market, in the beginning, the focus was on a lower side of electronics, logistic, food, or chemicals. But if you look at as a function of time now, there is a high focus on industrial manufacturing, automotive, aerospace, as well as now health sector. In our opinion, I think the automotive, aerospace, and health sector will see the great potential of growth using the 3D printing technologies. Now look at what are the material choice for these growth sector which I just mentioned, automobile or aerospace or health sector. A lot of technologies are known, for example, the polymerization, jetting, fusion, deposition. And if you look at the material choice, which are there, ceramic, metal, plastic, wax, paper, and now the live cells are also emerging. And since my interest is more in the thermoplastics materials and elastomers for the 3D printing, the photopolymerizations is emerging as also a choice for developing based on plastics, the 3D printing technology. The plastic and wax also have the jetting technology which can be used. Plastic also can be converted to the products using fusion technology like powder bed fusion. Deposition technique, if you see extrusions and other, can be that used. What does it indicate? It indicates the plastic will be the versatile materials, and if developed with respect to the properties suitable for 3D printing technology, then it can be used for using these all technologies which are available for the 3D printing. If you look the other part, the plastic part built through polymerizations, the plastic part built through the melting, where FDM and LS technology are also existing. And these two slides indicates that in India, if we develop the right kind of thermoplastic materials, there is a good opportunities for expanding or increasing the growth of these material using additive manufacturing. And that's why it is important that we should have our own material technology for these processing. And here I just try to show that in the morning you have heard more on the metal side, but our interest is more in the resin, polymer powder, or the filament, which are critical for many end-use applications. Furthermore, if you look at the thermoplastic material pyramid, and why I said that thermoplastic materials are versatile material of choice, and only the most important development which we need to do it, we need to bring the fine tuning of the molecular properties of these materials, physical, chemical, or other characteristics in a manner that it can be tuned to the 3D printing applications. Now, Reliance in the past 2 decades is very active in developing indigenous technology for polyolefin materials another. We are very much successful in developing the polypropylene products technology, first time in India, and now commercially producing the polypropylene materials in Reliance. Therefore, we thought we have large number of products which has come out from this technology which has been developed in Reliance from bench scale to the commercial scale in last 2 decades with different generations of product. We have extended that to the polyethylene as well as in addition to the polypropylene. And these successful developments have already been demonstrated for different products ranging in agriculture sector like the raffia grade. And here I want to emphasize the one example, which is that if we have our own materials technology, the molecular level structures can be tuned in a manner which is critical for processing. And in raffia grade, when we develop our own indigenous technology, we try to see how do we increase the speed line of processing unit. And we observe that there is a very good correlation between molecular weight distributions as well as the line speed. And therefore, we could alter the molecular weight distribution of the raffia grade in such a manner that we get highest line speed in processing machine. And this is one example which I try to show that when you have your own technology, lot of improvement, lot of designing of the material property can be done for different, suitable for different application. And that's why we went into impact copolymer, biaxial oriented polypropylene, or the random copolymer. And today, all the sectors are using Reliance polypropylene products based on indigenous technology. Even the random copolymers, which bring the transparency better than the other grade of material we could develop, because in 3D printing application, in some of the application, the transparency is also very, very critical. And now, with this knowledge of improving the transparency, we can say that we can develop the polypropylene materials for 3D printing. And that's why last few years, after development of all these grades for different sectors, we also initiated work on creating the reactor-made polypropylene. There are many products which are available in the market, which are based on composites or other. But we thought in order to make a more effective, low-cost solution for the 3D printing, we noted that the microstructures of polypropylene can be fine-tuned in a manner that will allow the polypropylene to be used as a suitable material for the 3D printing. And we are very successfully in developing few grades of polypropylene with the right kind balance of flow properties, stereoregularity, melting characteristics, crystallinity, the molecular weight. And that products we have seen that the molecular, in addition to the microstructure, the molecular weight distribution also plays a critical role for usable in the filament application. Further, as I mentioned, that transparency also plays a critical role in development of applications which are required for niche product. We are able to develop the polypropylene product very small spheroid size. And this is a spheroid size which allow the polypropylene to be more transparent as compared to if you have the polypropylene with a bigger spheroid size. And we could easily demonstrate that. We have used this polypropylene clay first in our FDM application, filament application, where we are able to produce a suitable filament which is useful for 3D, and we are also able to make some prototype as indicated over there. So this is a first prototype product which we have demonstrated using Reliance patented polypropylene products based on reactor technology. Further, the same way we have also developed polypropylene powders which are useful for the laser-based 3D printing. And those developments are also under progress. The next example which I want to cover, that today bioplastic is becoming a more important part in thermoplastic. We are working on developing our own technology for bioplastic, and our success of indigenous technology in polyolefins allowed us to move in the directions of bioplastic material suitable for 3D printed products. We are able to produce today one of the grade of bioplastic, which is a very early stages of development, but we are able to make a filament of bioplastic, and which we are able to then, using different design, we are able to convert into the product. And in my opinion, this is an area where the bioplastic-based thermoplastic elastomers or your other material will be quite a good solution to many of the challenges which are need to be solved for problems facing the society. So in summary, what I want to say that the fourth industrial revolution, the 3D printing or additive manufacturing, is going to play a very important role. And this is the right time when we all, the scientists, engineers, industries, academic, all should join together to ensure fast growth in this area of fourth industrial revolution, which is currently, because we could not catch up the third industrial revolution, but the fourth industrial revolution is the right time when we all should come together. And in this fourth industrial revolution, the material will be the most important factor, which any country should have that technology. And Reliance is able to demonstrate based on the past in polyolefin, indigenous technology development for different sectors, agriculture, defense, transportation, health, and also moving toward the solar energy. Also, we are moving toward that indigenous technology development. And the advanced polyolefin material, as I just mentioned over there, that we are able to succeed in developing the specialty polyolefin for 3D printing applications. For filament, we have developed the grade. We are also working on the polyolefin powders, which is essential for the laser 3D printing application. And next platform which we are creating is a bioplastic platform where it will be essential to design the product with a controlled life period in order to have the circular economy aspects and sustainability aspect also in mind for creating the solution for the society. We are looking for what is next. And as I mentioned, in the additive manufacturing, 3 platforms which are going to be critical: materials, processing, and the products. And synergy among these are very critical for developing indigenous technology, and these kind of inventions and innovation is going to make a much more bigger social impact in coming years. Reliance has already demonstrated few grades of thermoplastic polyolefins for 3D printing application, but we look forward now to create new technologies for 3D printing materials based on plastic, combining polyolefins as well as the non-polyolefin materials. And this kind of technology material development will take us to the next level of leadership in India for technology. Thank you very much for your patient hearing. Thank you.
Thank you, sir. With this proficient expert talk, we now come to an end of the keynote sessions. I request everyone present to join for tea at cafeteria first floor. Sharply at 4 p.m., we will start with the paper presentation, oral sessions at E201, E202, and E203. Thank you very much.